Swayam Prabha. Digital India. Educated India.
In this lecture, we'll be starting with a convolution sum, which plays an important role for finding the transfer function. Then we'll discuss why LTI system we should consider for linear control synthesis and what are the different assumptions we have to consider for finding the transfer functions of an LTI system. Then we'll discuss the lump parameter system, a system which you can write in ordinary differential equation form. And then we'll conclude the lecture. As you have seen in the previous lecture, the system is called LTI system if it follows the properties of proposition principle, and linear time invariant. Now let's consider the system. Let's consider the following system, following LTI system, where I'm applying impulse and we are having impulse response. Let me draw it. We have LTI system. So this, what I'm going to do it here, valid for LTI system only. So now we are applying to this LTI system del n and impulse, and we are having some impulse response. Let me denote it as Hn, impulse response. From this we can further write, del n, which is passing through the LTI system and giving the response Hn. Now, if you apply the time invariant property, if the system follows the time invariant property we can write del n minus k if the time has been shifted by k, and it should also reflect in the output n minus k. This is we have seen in time invariant property. Now, if this system, let me write this equation number 1. If the equation number 1 follows the rule of homogeneity, if equation 1 follows the rule of homogeneity, we can write x del n minus k xk h n minus k. This is, so it means the impulse scaled the input by xk, and also we are having the scaled output by xk. So I can write scaled the impulse and scaled the impulse response. Okay. So from this, we can easily say, let me write this is equation number 2. Hence, according to the homogeneity property, this equation 2 also follows the homogeneity conditions. So hence, equation 2 follows the homogeneity property. Now we'll see additivity to this to the equation number 2. Now, if the system follows the LTI system here, the system follows the rule of additivity, we can write a minor equal to, if you minus infinity to infinity, we can write xk del n minus k, and the impulse response k equal to minus infinity to infinity xk h n minus k. So this follows the additivity rule. This is clear. We have done before. Now, it is clear. Let me write this is term 1, and this is term 2, and also this is equation 3. And from this equation 3, the term 1, here term 1, I can write term 1. It's basically linear combination of scaled and shifted version of impulses. This is very clear because this is the scaled and this is the impulse, and that linear combination, because we can, this is really summation of the multiple terms. So we can say linear combination of scaled and shifted version of impulses. And already we know that the signal, okay, if I denote the term 1, if we denote the term 1 as xn, we can denote this is my xn and this is the yn. We'll talk later, just this moment. So now the hence any signal xn can be represented by shifted and scaled version of the impulses So this is very clear from, if we donate, this is my xn, then it is, we can write, if term one is shifted and scaled version of impulses, then xn also shifted and scaled version of impulses. Now, if you extend the same concept to the output impulse, the term 2 can be denoted by y1, similar to xn. And the same analogy also applied to term 2 as well. So what is the interpretation in this case? So we can write, if xn is applied to an LTI system, we get the output yn, which is basically, linear combination of scaled and shifted version of the impulses or impulse response. So you can write, if you're having xn as the impulse, which is scaled and shifted version of the impulses, and if you apply to a LTI system, and we have y1 or yn equal to, you can write k equal to minus infinity to k equal to infinity, xk hn minus k. So this is actually, if you notice, this is basically convolution sum. So here, so if I write, this is term 3, here the term 3 is actually convolution sum. So here it is, what is the takeaway from this part? So we can say that if you know the impulse response of LTI system, we can calculate the output for any input. So we can write from this part. So if you know the impulse response of LTI system, we can calculate the output for any input. This is a very important part in impulse response, and this concept we'll be using for finding the transfer function. Now consider why we have to look at LTI system for designing control system. So let me write, why LTI system we are assuming for designing the controls in this course. Let me write some points. First and foremost step is the system, this type of system are easy to. Second, A common mathematical framework can be used to analyze this type of system. A common mathematical framework can be used to analyze this type of systems. And also, the real life systems are not LTI in nature, but we can approximate those systems as LTI systems. And from these results, we can get the given inputs and can be used to analyze the properties of real life systems. The real life systems, so let me write, though the real life systems are not LTI systems, approximations the results we get for a given initial conditions and given inputs we can analyze and properties of real life systems. So that's why LTI system is very important to analyze the real life problems. The result we get, we can approximate the real life systems. Now, before we proceed to our main content, also we need some basics. So, what are the assumptions we have to consider in linear control systems? Let me write assumptions in linear control system. First assumptions we have to consider the differential equation, because as you know, we need the differential equation to design control systems. In control system, we need to have a mathematical model of the systems, and those mathematical model we can write in differential form. So hence, the equations or the differential equations we are using, that should be linear. The differential equations are assumed to be linear. And also, we'll confine our attention, we shall confine our attention to the to single input and single output system. So here, what you will be doing, looking at the system, will be considering system. We shall assume we are having single input and single output. If it is x of t, it is single input and single output, or u of t sum kind of, instead of X, UT can be your input and Y can be your output. So single input and single output system. So also sometimes we refer to as a CISO system, single input and single output system. And third part, we'll also confine our attention to the lumped parameter system. Attention to lumped parameter system. So what is lumped parameter system? The system with those systems whose behavior can be analyzed or described by ordinary differential equations. The system which can be described by ordinary and differential equations. And so these are the conditions we have to follow for designing control system for the linear systems. So let me assume we have a lump parameter system, lump parameter system. So here we can describe the system with ordinary differential equations, and we are having input to the system by input u of t, and we are having output from this system by y of t. So this is my output from this system. Please, one thing here we are going to consider natural system first, then we'll come up with the control. Okay. So here, let me consider a system. Let's assume a system. Consider a system which is defined by a ordinary differential equation. So let me write d4y of t dt4 plus a3 d3 yt dt cube plus a2 d square yt divided by d square plus a1 dy dt plus a0 y of t equal to u of t. So this is, we can say this is the lump parameter system which is defined using the ordinary differential equation. This system, if you notice here, we have some parameter or the coefficient in the system, or I can have another coefficient in place of this. Let me write some coefficient b not u of t. Let's assume this is u of t. So here, if the system parameters, because this a3, a2, a1, a0, b0, this is unknown parameters in the system. So if the system parameters, a3, a2, a1, a0, and b0 are time varying, Okay, first of all, this system I can say linear system. You can prove it. This system is linear system, amazing. But it is not confirmed the system is time varying or not. Okay. A time varying, if the parameters A3, A2, A1, A naught, and B naught are time varying, the system, or I think the system is still linear. Here, a system with time varying parameters is called time varying systems. This is very, very important. If the coefficient of this system are changing with time, then we can say the system is time varying system. While a system whose parameter are constant with time is called time invariant system. So if you want to check, you can take an example, something like that, and you can verify with the concept we have discussed before. Now, from this system, let me write this some equation. Let me write this equation number one. In equation number one, for a given initial condition, for a given initial condition, the solution of equation 1 is a function of time. I guess this part you have done in your mathematics, because if you solve like some simple OD, for example, x dx dt equal to minus 4x, and you have initial condition some x naught equal to sub 4, so we can come up with the solution x of t e to the power minus 4t into 4. So this is the solution basically, right? This is you have done in a mathematics. So if you look this solution, it is basically time varying, right? It is this x of t is a function of time. So now, however, let me write, however, there may exist special solutions which are constant. This is very, very important point. There are special solutions. And such constant solutions for an unforced system are called equilibrium point, This is very, very important part in a control system. Until unless we don't know the equilibrium point, we can't come up the system in linear form from the physical systems. So if you notice here, it is some term I have used here, unforced system. So it means if you look in our original system, this is our original system equation 1. So with the effect of u of t here, my system is evolving. So here u of t act as a force or input to the system, and due to which the system propagates. I can say, if you want to find the solution of the system, we have to assume the force. We can assume the force is 0. So not you have to, you can assume. So now what you will do is, to solve this equation, you can write d4 y of t dt4 plus e3 t cube y of t d t cube plus a2 d square y of t d t square plus a1 dy dt plus a0 y of t. So equal to 0, we have to assume. And if you find the solution of this differential equation, there can be some special solution which we are calling equilibrium point. In some cases, this equilibrium point also we can say, let me write, this equilibrium point sometime fixed point or trim points. So there are different terms we are using. Let me write one point. Why you are calling this fixed point or trim point? Because the system continues to be at rest when it already at such points. It is very, very important for line. So at this point, the system will be remaining at its original or natural behavior properties. So this is how we can define how we can come up with the equilibrium point and how it is defined. So most of the control system we design keeping the plant at this fixed point, because what you will do is, if the system, this is your system, for example, my some kind of, let me assume the pendulum system. This is my pendulum. The pendulum, if it is the two position, it can stay constant. If it is vertically up, this is the position, one position, and it can stay also this position. So there is two equilibrium point, this position and this position. So now we have to design a control system in such a that if in the system, I mean the pendulum disturb, suppose from disturb to this point, for example, we have to design the control system in such a way that this pendulum should come back to the initial position. But in this case, this is basically stable, I can say. Even if it disturb, it will come back to automatically here. But this is basically, this is my initial equilibrium point. If it disturb, the system should be able to come back to the equilibrium point. This is my equilibrium point. So we'll be talking in more detail after some time on this example, how it working. So our control system, we have to design in such a way that the plant at one of its equilibrium point should stay. And suppose it is the use of this kind of system are everywhere, like missile, aircraft, like autonomous car. And this is how, I mean, we'll analyze or describe, or we need to design the control system around the equilibrium point. And so now we'll be talking on how we can find equilibrium point and how we'll check the system is stable or not. Hence, equilibrium point plays an important role in designing control system. Since most of the practical system are nonlinear in nature, but since in this course we'll be designing linear controls, so we need to study the equilibrium point and how will make the system stable at the equilibrium point. When the system has unstable equilibrium point. With the application of control, we can make system stable. In the next lecture, we'll be talking on equilibrium point and how we'll study the stability of the equilibrium point of a system. So thank you very much. We'll continue from the next lecture.